now introduce a new magnitude into these space-time diagrams, that is the energy. We will do so with kinetic energy. Remember that a body, a particle like a proton, for example, at rest has no kinetic energy, but when it is in movement, it has a kinetic energy. We will use all the times the same mass, so as to emphasize the effect of energy in what follows. So, we will represent this in space-time diagram. This is the word line of a proton at rest. It has no kinetic energy, but if it is moving, it can have some kinetic energy or even a very great kinetic energy if the speed is very great. So, we will use this idea in the space diagram of a collision between two identical protons with equal speed. As we have seen, the center of mass is in the middle of the space-time balance of the instant. Now we make a classical relativity transformation to the reference system of this proton, so that it has lost its kinetic energy and the other has a lot of kinetic energy. Now the situation is no more symmetric, but we will check the effect of this energy on the situation of the central equilibrium point. We know that in relativity, the effect of the transformation of the change in movement to rest does not affect the instant at all. The instant remains unchanged, because it is the reality, and for classical physics, it does not depend on the movement of the observer. So, we have seen that in this classical collision, symmetrical collision, the displacement to the reference system of this proton does not affect the position of the center of mass. That is, we can increase energy and the center of mass will not be affected. The center of mass is all the time in the middle of the instant, in spite of the presence or lack of energy. This is a classical result that energy and mass are different magnitudes, and we are not surprised by that. But if we now make the Lorentz transformation for the same situation, we will see what happens. Now again, the symmetric collision between two protons, and we make the Lorentz transformation. Now we know that the instant is also inclined. When we make the transformation, the instant also gets inclined, so that the position of the middle of the instant, this is the instant before, but now it has changed, and we must draw this line to the new instant, and it is displaced to the mass with energy. So, let us see it again. Symmetric collision, displacement to this reference system to one of the protons, and the instant inclined draws the center of mass, pulls it to the greater mass. So we can make this. This is our instant, and in our instant, the presence of energy pulls the center of mass. This means that mass and energy are the same magnitude, because they can be added. And this is the famous equation by Einstein, E equal mc squared. The effect of c squared in our natural units were, remember, the speed of light was the unit, c is equal 1, c squared is also equal 1, and mc squared is equal to m. So E equal mc squared in natural units becomes E equal m. And in these collisions, now, what happens with the energy? In the classical collisions, the lost energy is transformed into heat, but between particles, this is not possible. And if the energy is enough, it can be converted into new particles. We can transform energy into mass. This is done at the great accelerators, like the CERN in Geneva. And to the contrary, we can also transform mass into energy, and this happens all the time at the stars, like our Sun, who are losing mass very slowly, but in this process they produce a great lot of energy, and this energy we receive it as the radiation from the Sun, the light. So light is originated in the stars from their masses. To keep with these ideas in mind, we can make the following sentence. Incline the instant to be aware that E is equal to m times c squared. Now, with the song, incline the instant to be aware that E is equal m times c squared